So we have a homework due. The homework due on Thursday. Most of it should be reasonable. I think it's some of this you might have seen somewhere else. But you guys said have you done relativity somewhere else at some little depth? Right, and this is the introduction to relativity in a sense. So most of it you must have seen somewhere. Other it's mostly Lorentz transformation. Next week we will do, or next class onwards, we will do the dynamics properly. Or first the kinematics, where you go beyond what you see in undergraduate physics. So that should be more useful. And midterm 2. It's March 29. Okay, so what we have introduced as of now is that just because there exists one effect, if you want, it's the speed of light, just because speed of light is the same in two different frames, there must be Lorentz transformation. Galilean relativity cannot be true. Lorentz transformation exists. So now from this point on, we will say that that's Lorentz transformation exists. And what else can we conclude? Lorentz transformation is we're doing one dimension Lorentz transformation. That means that let's say z prime or x prime, y prime, z prime, and the fourth coordinate is CP prime, right? That's just to make the dimensions the same. Speed of light times time is has a dimension of length. So if motion is, so the relative, the two frames that we are talking about is, so we have one frame that measures x, y, z, and t, x prime, y prime, c prime, and t prime, and the other frame is moving with a speed v in the z direction. So that's your z direction, z prime if you want. So you're saying z prime and z are aligned. And this coordinate measures x, y, z, and t. Think of it as one car going in the z direction relative to you. If one of you is sitting at rest and I move, I travel in a car in the z direction. Oh, this is z. That's what it is. And then we said if this is v, I can define beta as a measure of v, so that's v over c, and gamma is equal to 1 over 1 minus v squared over c squared. Is basically 1 over 1 minus beta squared. So that's equal to gamma, and this is 0, 0, beta times gamma, 0, 1, 0, 0, 0, 0. Oh no, what did I do? It's not because my z is somewhere here. So all this has to be 1. That's 1, 0, 0, that's 0, 0. So x prime and y prime doesn't get affected. So this is gamma, beta gamma. 0, 0, beta gamma. And that is x, y, z, c times 2. In general, we should be talking in terms of more complicated Lorentz transformation. What if this is moving in in some arbitrary directions, and this is itself so counterintuitive that you begin with this and stick with this for quite some time. But at the same time, one can generalize this, and there are non-trivial effects that comes out just because you're moving in different direction. As you see, the main piece is in here. So often you confine your attention just to this. You talk in terms of two-dimensional transformation. So we will often talk about C prime, T prime is equal to gamma, beta gamma. Oops, gamma. If you are to take the inverse of this is just got by taking beta, replacing beta with minus. So that's all there is to it. And here we would like to see what are the consequences of this. So first thing we can do is, which we sort of talked about last time itself, is that if you were to start with z prime square minus c t prime square, right? If you were to evaluate this and replace this with this transformation, substitute this, we did this last time, and you can show that this is equal to z square minus c square t square. And we compared this with rotations. In rotations, what you would do is, if you were doing x prime and y prime, this is not the same x prime, y prime, this is an independent transformation altogether. If you were to do rotations, x prime plus y prime square will be equal to x square plus y square. And we said, okay, how do we interpret this? So you would say, okay, I have a frame, and let's draw a circle. Like just for reference, let's draw a circle. We will interpret this as x square plus y square remaining constant. So that's your x and that's your y. and let's not say x and y. This is some what do you say, I and j, right? X or x hat and y. X hat and y. Just to clarify that, that's just a direction, because I want the coordinates here. So that's your x comma y coordinate. In this frame, that's a very standard thing we do. Now let's say that I rotate this frame by an angle theta, and this would become like this, right? So that's your x prime, and that's your y prime. I've rotated my axis, so that's one way of looking at it. But in this new frame, this point has moved in the backward direction, right? Instead of looking at saying that my axis has moved, I can say that my coordinate has moved in the opposite direction, right? That's another way of looking at it. So there is, in the new frame, the same point will have x prime, y prime. Is that clear? Okay. So let's say that this way of looking at it, what I've done here is that there is a coordinate here, which was earlier xy, and now I moved my axis to x prime and y prime. Now let's say that that will be called, my point remains the same and my axis is moving. Okay, so let's now have another way of looking at this. The same circle. This is my x prime, y prime, sorry, xy. Notice that earlier this xy is closer to my y-axis. Relative to this new frame, my coordinate is a little farther, right? And that distance is actually that angle theta. So what is happening is that this x prime, y prime, there are another point on the on the sphere is connected through a rotation. Is that clear what I'm saying? X prime, Y prime here on this circle, take any circle, take 2 points, one is XY, other is X prime, Y prime. This X prime, Y prime is connected to this XY through a rotation. So that means to say that, let's say, this is my rotation. Let's say that's my phi or theta, let's say, or phi, let's say, right? So X prime, Y prime is equal to cosine of theta, sine of theta, minus sine theta, cosine of theta, times xy. So there exists an angle which is the exact opposite. I wrote phi there. There exists an angle phi by which I can rotate, which means to say there exists this rotation where these 2 points are connected. So every point on a circle can be reached by making a rotation. Is that clear the way I'm interpreting that?
So what about like direction of if it's going to go like counterclockwise or clockwise?
That should be plus or minus phi, right? In this case, I'm not very clear which one it is. Okay? So let's see. So if I start from xy and rotate it, correct? So x prime, y prime is, how can I connect this? Let's say, if I make a 90 degrees, x should become y. Is that clear? Mm-hmm. So if I go in the clockwise direction. So let's see. So x I start with y, right? So this should be 0, or this should be 1, that should be 0, and this should purely become 1. So that should be 90 degrees. So this way of rotating apparently is clockwise rotation. Right? Let me check once more. Okay? Because cosine of 90 is 0, sine of 90 is 1. Yeah. So if I use this rotation, I do get x prime is equal to 1. So this way of writing apparently is clockwise. But I'm saying those are details as to what exactly is the transformation. What I'm trying to convey here is that every point on the circle is connected to another point on the circle by a rotation. There is nothing as far as or if the system was built out of this construction, x squared plus y squared, right? There is nothing special in this frame. I can rotate in any frame. As far as everything is on the circle, if the physics is happening on the circle, that means by this construction, I can rotate it and I'll get the same thing. There is nothing special about x and y, right? That's just our choice. Is that clear? Like that's my simple statement. If you see a construction in your experiments which has only x squared plus y squared, then I can rotate my frame and write x prime squared plus y prime. Right? That's another axis. And there's nothing special in it. And you could go to any frame and that's perfectly okay. Is that clear? And that is given by either you can say that this is a rotation of the axis, or you can say there is a rotation of the coordinates in or any point on the circle is the same as far as physics goes. It's just a matter of which axis is you're looking from which axis, right? Every point on that is the same if you're talking in this construction. If you talk about x, of course, x is different for in different frames. In fact, that is the point that, I mean, another way of looking at it is if you were to think about relativity, if you say that I measure x here, like think of, let's stick to this because this is very intuitive, right? If I were to say that all my physics has to conserve this, x squared plus y squared has to be invariant, okay? And then say that, okay, I measure my x. I measure an x, you measure another x. And you say that, oh, my x doesn't match with your x. It's not supposed to. The physics only says that x square plus y square has to be invariant. Right? In this case, you can measure x, but then provided that x remains the same. X does not remain the same, right? So you would not even try to match. Would you ever say that, oh, I measured the x component of this coordinate and I do another measurement of x coordinate in a rotated frame and we try to match each other, right? That's meaningless, right? And we would not even try that because we understand geometry very well. And you say that, oh, that's not supposed to match. That's because you rotated yourself. If you go in the rotated frame, then it will work, correct? And there is no surprise here. Right? You never match your x with my x, correct? Now let's do Lorentz transformation, right? The Lorentz any questions here by the way before?
So is it, I mean, is it only in here, I mean, circle, or you can find it in other configurations?
As far as, see, this is an invariant structure on a circle, right? This is very simple in the sense I'm saying that I'm going to do physics where x square plus y square is a constant. I'm going to talk about those physics where x square plus y square is a constant. That's very restrictive physics, correct? That it has to be rotational symmetry. That's what we mean on a circle. Whether I look in this direction or in this direction, it should be the same. That's very limited. But if you limit yourself, then there is no point in measuring x component and comparing with another x component. Right? They won't match because they are rotated. Right? But x square plus y square, you measure your x square plus y square, I measure my x prime square plus y square, they will always match. The length of a rod will always match, right? Because it's x square plus y square. And that's not a surprise at all because we understand intuitively what the geometry is. Clear? I'm going to try to take this into Lorentz transformation and see that see the analogy. Okay, try to see that. So now we are saying that instead of x square plus y square, z square minus t square. It's just I chose my z and t separately. It could have been x square minus, let's say, but one is time. Okay, let's keep the time as it is. It could have been x also. That's just too hard. Now let's see what does this equation look like. And for it's generally z is put on the x-axis and c and t is on the y-axis. This should be interpreted as x hat and t hat. So this is the direction of z and that's the direction of time. And if you were to go at speed of light, so if you were to go at speed of light, that would be this line. Is that clear? Right? Because the distance, if you go 1 unit here, 1 unit in the y direction, that slope is c. So that will be, that's the direction of speed of light. Is that clear? No. Okay. So how do you say? Speed of what I mean? You start from here. Suppose you're at rest. How will it look like? If you're at rest, then you are, let's say this is origin. You just sit there. And as time evolves, you're still at z equal to 0. That's your path. You're at the origin to begin with at time t equal to 0. At time t equal to 1 also you're at the origin. At time t equal to 2 also you're at the origin and you keep going. That's at rest. Now let's say you're moving a little faster. So as you move at time t equal to 1, you move a little x to the right. So that's also a path of a particle. But now what is its speed? Speed will be how much distance you go here divided by how much distance you go here. Right? And there is a c in there. Right? So what you measure will be beta over c, like velocity divided by c. Is that clear? So delta z over c times delta t. That's how much distance you go. So that's your beta over c if you want. Correct? And beta over c has to be always less than 1. So this is going less than c. If you go here, what's the problem? Now delta Z is larger than delta T. Right? So beta is greater than Z. Is that clear? So that's not possible, right? Or unless you want to consider situations where things go faster than, like we will have issues with faster, or maybe we should begin by saying, why are things not allowed to go faster than light? Any reasoning?
What are the questions?
So can we go faster than light? So you will always hear that, yeah, no, that's, but then why not? Is there a reason?
I think because we can measure any velocity more than light. That's why I think they will come.
Surely, yeah, I mean, you're right. I mean, we don't see anything that is going faster than light. That's surely a reason for it to do. But the question you can ask is, does physics principles get violated or not? And here is an, I mean, I don't know what exactly is the reason, but I would argue the following, that we use logic to do things. Like we say that, okay, if this happens, if A implies B, B implies C, then A implies C. That is a logical deduction that we depend a lot in mathematics and physics.
Propositional.
And logic doesn't work very well when you go faster than light. For example, if, I mean, as simple as if you go faster than light, I think that example typically you gave you that, let's say you're born here, A, right? You're born here and you emitted a light when you were born, light fell on you, correct? And then reflected, right? So this, in if someone were to view this here, they will see that you're born. Correct? But now if you can go faster than light, apparently, like you're born here, light went there, so you overtake this light, and then you see yourself being born, right? Which is kind of not causal. It's very quickly you can say that you kill yourself, and then you're still alive in the sense that you can observe yourself getting killed. So all these non-trivial things are counterintuitive or not logical, right? It is not easy to put these things together the moment you say things are going faster than light. And it is messy enough that you're not able to proceed further. Right? It's like you're seeing movies where there are things coming from future to the past. It's okay as a movie, you build those things, but when you question that logical procedure, how does this very quickly it doesn't make sense, right? And you cannot process it. And I think it is that reasoning being, you're not able to proceed in that logical argument that you don't even want to entertain, or you're not able to entertain. So tomorrow, if you can be clever enough that, okay, logically one can build these things, maybe it is allowed. It's just okay to at least theoretically pose the problem that you can go faster than light. But in my understanding, you cannot even, it's hard to even pose that question. But having said that, okay, so we will have things going slower than the speed of light. Okay, so physics in this course will go slower than speed of light, or at the most at the speed of light, and that will be the light itself, right? So this is not allowed. We cannot go. So anytime you see a particle going this way, it's okay. But now let's say, what about, so this is one particle. What about this? There is something sitting at z equal to a constant. How will its whirl line look like? It's just sitting there. How will it look like? It just will go straight again, right? It's a straight line. And then you can ask the question, okay, so there is A here, there is B there. How can A communicate with B? And by communication, I mean not just talking. How can A interact with B? Remember, interactions, for example, electrostatic or gravitational interaction, is a communication in the sense that if I'm a mass m, you have another mass m, I have to tell you that, see, I exist. So that, come on, attract, right? We have to pull each other. For that, you have to know that I exist, right? And then the question comes, but interactions go at speed of light. So when can A and B interact to begin with? Let's say both A and B were existing, right? They were born right just now. A and B cannot interact because they don't know each other yet. So it takes speed of, so you send a signal at speed of light, but it takes time, right? It will reach here at this time. Time has to go, right? And the same thing here, this can be, but both if speed of light come together, both travel at speed of light, then maybe it can be done at a shorter time. But if you want to communicate, if B is at rest and A is sending a light signal, the first instant it will come to know is here when they interact, right? So the whole logic of when you will know that the other person exists is very counterintuitive. Think of the universe itself. It gets very hard the moment you think of the universe itself. Let's say, like it's very easy often to say that, oh, what's the radius of the universe? And you say that, oh, I don't know. I mean, maybe it's finite, maybe it is infinite. But it has been experimentally tested that there is a finite time for which the universe has been here. At least there seems to have been, or we don't know whether there was a Big Bang or not. Everything seems to be moving away from us, right? And then you can move it backward. If everything is moving away from us, you extrapolate backward. It seems like at one point they were all at one point. So that's what you mean by Big Bang. You can calculate the time it took for that. How much time is that? What's the age of the universe?
600 billion years.
600
billion?
600 million.
Billion.
No, less than that. Significantly less. It is known to about 3 6 digits. It is 13.6 billion years. That is about 10 raised to 17 seconds. Okay, and this is known to at least 2 significant digits, if not 3 significant. That means to say that there are various data that comes and we are sure that it's true to that much. Okay, that means that if you are sitting here at the origin, okay, now yeah, suppose we accept that there is a finite time, right? We are sitting at the origin, and let's say that we are not even moving, and at least in one frame we are not moving. That's your z, that's your c times t, right? So that means somewhere here, right? That's the time. That's 13.6 billion years backward in time. That's when our universe began, in a sense. And then you can ask, what do I mean by I know that some signal has come from there? So the fastest signal that can come from that universe is at speed of light. So let me say I go backward in speed of light. I project it backward. So this is that line, the epoch, if you want to say. And if I go backward in time, this is the only 2 points where it can reach. If any point is within here, light can reach here. If there was a point here, for example, I would not know, at least not today. It will take more time for it to reach. So irrespective of whether the universe has a radius or not, there is only a finite amount of universe that can interact with me. Like even gravitational, it cannot attract. Is that clear? Right. So those are counterintuitive statements that come from here. So I'll let you guys think about it. Just because speed of light is, or speed of anything is smaller than speed of light. Those are the consequences of, okay? Those are non-trivial consequences, but we want to talk about something more reasonable. Like the moment I talk about universe, it is already speculative, the timeline of universe, even though it is measured to two or three significant digits, it typically gets a little harder to interpret. So we can go to more basic things which are more measurable, and let's talk about that. Any questions here at this point? The only thing I have tried to do is I have tried to draw world lines. These are called world lines, the path of a particle, and I've said that if there are two such world lines, how do they interact with each other? Or I mean, this is, I'm digressing significantly. I want to compare this to that. But I can tell you one more thing, which is sort of counterintuitive. I typically give this as an example. So I gave you a scenario where if time is finite, there will be regions in the universe which will never be able to interact with me, even gravitationally, they cannot pull me, right? And there is another counterintuitive thing you can have. Let's say this is your reference. That's your. Let's say if I were at rest here, I go straight. Let me say I start accelerating in this direction. Okay. That means to say I first go a little distance, then I go faster and faster, and then let's say I go like this. Okay. Is that an allowed curve? I say that a path of a particle is this. Is it okay? Yes or no?
No.
No, and why is that?
Beta is greater than C.
Where is it beta is greater than Z? Because this is beta is 0, right? Here. Here, the slope of this line is beta, right? That's 0. But you guys are right. Because as I go, so this is 0. That's 1. That's when it goes speed of light. This is going way faster than light because it has crossed this. Is that clear? Right. This is 0. This is at rest. Then I start going faster, faster, faster. But very quickly I go too fast. It's beyond this point, I'm going faster than speed of light because that's parallel to that, right? And then I start going fast. So that's not allowed. But then I can. What about this? So now let me ask you guys again. So this is a hyperbola. Is that allowed? Right? That's allowed because the slope never goes faster than speed of light, right? And that is accelerating. It is actually going faster and faster, and more delta Z is being covered in each time. This is called hyperbolic version. This is that version of uniform acceleration, a relativistic uniform acceleration, when you take a parabolic or hyperbolic path. But let's say that's going that way. So this is accelerating, and let's say it starts from the past, right? So this is your current time. A particle comes from here, like this is your Z, and it goes there. So how will you interpret this? A particle at very large time was very far away from origin, right? It approaches here, so it is approaching here, comes to a rest, so it is falling in a sense, comes to a rest, and then goes back. So it's like saying there is some gravity acting there. You throw a ball, it slows down, comes to a stop, and then starts falling. That's it. Okay. So that's a particle, but it is possible to, let's say there is an aircraft that is actually moving in that way. Okay. Let's say there is another aircraft that's moving in here in this way also. Is exactly opposite direction. And let's say this is A, that's B, that's particle B, and there's another guy sitting here. That's your C. And now let's say we ask, how will A and C communicate with each other? If A has to communicate with C, the best is to use speed of light, right? You will send a signal and you ask, when will A be able to communicate with C? Let us say it starts sending a signal from here. So go parallel to this. So this is, so So if you start send a signal from here, it will reach here, right? Now ask the question, how will A and B communicate? And it turns out that it cannot, right? It cannot interact with it. Even if you were to send a signal from here, it can only go speed of light. It never touches this. So it cannot communicate. You send a new signal from here, it never touches. So A cannot communicate with B. And that has this counterintuitive. If you imagine this, you're saying that there are two particles, because of their specific motion, apparently they will never be able to interact with each other gravitationally. Right? Which is, again, you don't expect that, right? They might come very close. Like this might be really close. This might be 2 meters. Right? So someone comes here, someone comes there, they never see each other. But there is a third particle that sees them. C sees A, C sees B, but A and B never see each other. Right? So that's a counterintuitive statement again. But those are all because things are confined to going slower than speed of light. Right? So with that counterintuitive features of things going slower than speed of light, now let's look at this constraint alone. And we said earlier that if I have a constraint like this, I can imagine things to be on a circle. Now I do the same thing here. And I realize that this is nothing but an equation of a hyperbola like this. Can be any of this hyperbola. Any of these 4 hyperbolas will have this quantity fixed, a constant. Okay. Except that here, this has to be when if Z is greater than C times T, that is here. So let's say this is Z, and that's CT. Here, Z is magnitude of Z is greater than magnitude of CT. Right? We measure with respect to the origin. Is that clear? Right. This length here, if there is a coordinate here, this length will be greater than this. Right? Same thing on this side also. But here, magnitude of Z is less than magnitude of CT. Clear? So if this quantity is positive, then you're either on these two. And if this is negative, you're on this lines. Okay. Whenever this is greater, so this is greater than 0 is called space-like. And less than 0 is called time-like. And equal to 0 is called light-like. Is that familiar words? Is that clear? So if it is greater than 0 because position is larger, space-like, time-like, and right on this, that is a light-like. Let's for a moment say that this is time-like and Z and T are here. This is my Z comma T. I make a Lorentz transformation. This is my Lorentz transformation. I measure something and I start moving with respect to another frame and I measure the same object, same event. Okay. But how will I do that? I use the idea from the circle. I don't do anything. In that new frame, whatever I do, it is something, another point on the same curve. Whatever be my velocity, there exists a point on this curve which will make it, which will allow this transformation to be true. Is that clear? So this is my original point. This is my second point, right? Here, original point, second point, right? Or here we will do this. Like these 2 points are connected by that. clear? Okay, if that is the case, then you can make some conclusions. Oh, yeah. So now, here I made another statement, right? I said that if x square plus y square is fixed in your system, you will never compare your x. Now, we have seen just because speed of light is the same in two different frames because of Maxwell's equations, two different frames measure speed of light the same. So Lorentz transformation has to be true. So this has to be fixed. Our universe obeys this. It is like saying that our universe obeys this. Your experiment measures obeys this. In our universe, there is no choice. You cannot change this. If this is fixed in one frame, it has to fix in one frame, and we are stuck with that. That's the law that governs us. Now let us say that one of us says that, oh, I measure my time, you measure your time, and you're moving with respect to me. And you say that, oh, I measured my life, for example, right? You're moving. You take a spaceship and you move. Let us say at 3 meters per second, not very fast. Okay? You measure your life span, age, you measure your age in your spaceship. I measure your age on Earth, right? And I say that I compare that, right? That's meaningless. We shouldn't be doing that. We always do that, right? You measure it in your life, I measure with mine, but we are comparing t and t prime. That should never be done. That's like comparing x prime and y prime. They will not match. Is that clear? Especially if you're going faster. It turns out that if you're going at 3 meters per second, the error you make is in the 5th digit. But we are not even supposed to do that. Logically, that's insensible, or it's not logically correct. In the same spirit as you will not compare x prime and y prime. Right? What you should compare is what is constant. Measure how far you're traveling between those two events, and measure your delta z, measure your delta t. And that quantity, if you compare, that's okay. You can measure time, that's okay. There's nothing wrong in measuring x, but then don't compare it with another person who is measuring x prime. They are bound to not match. Right? Same thing with time. You don't compare times. You don't compare z either. What you can compare, if you're matching results in a lab, you measure this quantity and then compare it. Okay. Is that clear? Right? And that's the idea of length contraction and time dilation. Right? In one frame, you measure time. In another frame, you measure time prime. For example, these are two different frames, right? This frame, there is a frame here. There's a frame here. Time is this. This is your time. In this way, that's your time. If you go farther, if you go faster and faster, your time keeps dilating. Right? And then you say, oh, it doesn't make sense. There's a paradox here. No, there's no paradox, because you're not even supposed to match. Right? You're not supposed to match times. That's it, period. The paradox typically comes that, oh, okay, it seems like if I'm at rest, you are dilating. If you are at rest, I'm dilating. All that is constructions you can make. But once you accept that this is invariant, there is no way you can go wrong. Right? Measure your time, measure your position, you will be okay. Right? You will always be on this curve, and that will be perfectly respected. But I did mention something here. There is one conclusion you can make. Right? So, yeah, so let's be in this. There is a, notice, if you're on this curve to begin with, that means you're time-like. Right? If you're somewhere here, that means that this will be less than 0, right? It's time-like, it will be less than 0. If you're on this curve, you can say that there exists a frame, there exists an observer who will measure your time to be purely time-like in the sense that two events are happening at the same time. That means you're at rest with that observer. It's purely time. Is that clear what I mean? So for example, if I have this event, right? This event I can say is with respect to the origin. Origin is always invariant, right? Between this origin and this point, that's two events. This is where you were born. That's where you are currently. And there is an observer relating to this. You would say delta Z is this, and that's your delta T. How far have you gone? How long have you lived? Correct. But you can always find a frame that is with respect to one of the frames. You can always find a frame that is this, who would say that, oh, you didn't move at all. You were born and you're still here, right? And your time evolved this long, right? That's a true statement. And you can always have a frame. If there are two events that occur, you can always find a frame in which the two events happen at the same position, but at different times. If they were local, or if they were causal, that means if the physics is obeyed, one happens after the other. Right? If I shoot the gun and someone dies, the death has to happen before I shoot the gun. Right? That's causal. If I shoot the gun and someone dies, the person has to die after I shoot the gun, right? It cannot happen before. Right? So what it means is that, so again here, it means that there exists a, so delta Z and delta T. A delta T is always greater than, or how do I explain this? Okay, I can tell the opposite, right? Let's have a contradiction. Okay, so let's have a contradiction. So let's say that, let's say you're in this region. Okay, so I claim that me shooting, so I shoot at the origin and the death happens at this time here. That's future, right? So I shoot, that happens here. So that's the first event. So event one, that's event two. Like the gun has been shot, that's someone dying. Okay. If that was true, so I just randomly picked it to be at this point. Now I claim that this cannot be true because if this is true, I go to another frame. Right? In this frame, I'm here. I go to another frame, that's somewhere here. I reach here. Right? Here, according to this observer, someone shot the gun in the future and someone died here. Is that clear? Future, that's timeline, right? So gun was shot here, but the death happened here, which is below in time. Time has to always evolve, right? So what happened? So you say that this is not possible. Any causal things, causal means something happening and something, an effect, cause and effect, cannot happen in space-like. Space-like is not causal, right? If so, this is not possible. Okay, so in this frame. So what can you do? So where is causality, right? So all world lines has to be connected by this part. Now you see, if you're here, right? Now this is future, that's your past. And even the best I can do is this. But wherever you go, whichever frame you go, always the cause and effect is maintained. So because you want to respect cause and effect, you say that everything that is happening in real life should happen in this scenario. A particle can go in this manner, remember, right? Like a particle can go along this path. We are just saying that these two events cannot be connected by a Lorentz transformation. The same event cannot be seen by two different observers. Here we are talking about two different observers. A particle could go along this path. Don't confuse between that. Earlier I said a particle can actually go along that line. So that's different physics. So this is called simultaneity in the sense there exist events which are not simultaneous, like anything that is space-like. Here it is not simultaneous. I go here, it is simultaneous. In fact, I go further down, it is not, I mean, it is negative simultaneity, right? The cause and the effect has become effective cause, right? So space-like events do not respect simultaneity, or simultaneity is just not a concept true in relativity. Simultaneity in one frame, the moment you move around, it can change. Simultaneity is just not possible sense. Okay, that's few of the concepts. Questions? Yeah.
So there is like a negative time.
The negative time is here. Yes, that is it. So this is your 0. So I set my t equal to 0. Past. So this is past. Future. That's where you sit.
So, like considering the finite age of the universe, how would you have a negative time at the beginning?
This is with respect to you.
Okay.
Correct.
Mm-hmm.
So if the universe started here, someone sits there.
Mm-hmm.
With respect to that, everything has to happen inside this light cone. So that's the light cone. Whatever happens, anything that is cause and effect has to happen inside this. And let's say, let's go a little further in time. Let's say there are two things, like this expanded and then there are two parts. Now there is a light cone of this and light cone of this. So light cone of this says that anything can happen here, light cone of this happens here. So whenever, so all the overlap, all the interactions will happen in that common region. But there are, if you go to the left with speed of light and if you go to the right with speed of light, then you may not be able to communicate. Right? But these two, there is a common ground where you can meet.
So is it safe to say that the snapshot that we have of the universe in the past is like microwave background radiation is unique? Like we'd have to be at this current time to be able to.
No, see, this is where you will start getting into paradoxes now. So what is the cosmic microwave background is you are sitting here, and so it's exactly this diagram, right? So you're sitting here and you go back in time, right? And notice this is in this direction and this is in this direction, and light is coming from here, right? So you collect a sample from here in this region, you cut everywhere in this region. So this is all light coming in from here, and you collect them. Great, that's good. And it turns out that they all have constant temperature. They all have perfectly the same temperature. In fact, even the anisotropy is predictable. Okay. So now you say that, okay, that's good. But on the left side and the right side, it's good to say that, okay, they all got homogeneous. They mixed up very well. So the universe came to a uniform temperature, thermodynamic equilibrium, and that's what we are seeing. That's the idea of cosmic microwave background. But how can the universe on that side have interacted with this side to begin with? Like they have interacted with me barely. But from this corner to that corner, it could not have problem. Right? But then cosmic microwave background happens not at the 0 epoch. It is only after a while. I think it is about years. I think it's about 300 years. So cosmic microwave background is okay, but if you go further back in time, you will have situations where one part of the universe should look different from the other part of the universe. because they just have not reached equilibrium. For reaching equilibrium, you have to interact, right? So they have not. So there are different bubbles of universe, if you want. I think that's what your question is, probably. So what you're asking is cosmic microwave background unique? That's your.
Yeah, to our specific time, like going back 7 billion years and then doing the same thing, would we be able to get a different picture of the universe because of this limit on C?
Or here is what I can say you see in cosmic microwave background. In cosmic microwave background, we see that in every direction that you look, right, whatever be the direction, you see exactly the same temperature. The black body radiation that we come from this corner of the universe to this corner, or for that matter, in any direction, is exactly the same to great accuracy, like to 3 or 4 significant. I mean, they don't measure in sig digits, it's measured in poles like dipole, quadrupole, and so on. In the spherical harmonic expansion to about, I think, third L or something. I mean, very large L, they can match it. It is too good a match. And then you say that, okay, so uniform was homogeneous in that at that epoch. But remember, that's not 0. It's, I think, only at 300. Cosmic microwave background is a signature of about, I think, 300 years or something. And we haven't been optically able to see this, optically, or even, what do you say? Using a telescope, we have not been able to see that far. But what we could do is that we can wait for the signal to reach in our detector, or how do you say this, which is also, yeah, I think in the, yeah, it's probably, yeah, I think it is the same. Yeah, I shouldn't say that we have, like, that's the big deal with James. Yeah, it's not. I mean, okay. So in the microwave wavelength, you see this information coming from every direction. Now you can ask that the recent satellite they have sent, or sorry, the telescope that they have sent, James Webb Space Telescope, that will be that is kind of a successor of Hubble. They are advertising it as that will be the closest you will be able to see in this cosmic. It won't be able to touch cosmic microwave background distance, but you will be able to be in that range at least. So it's a big achievement as far as telescope goes, and you build that and you go there. So in that sense, it's a, and there will be a lot of clarity. So it will be another way of measuring the same quantity. And I don't think I've still answered your question, but yeah. Then these are called horizons, if you want. Different horizons, can they talk to each other? No, that's a valid question. Okay, so I haven't specifically done what is needed for the homework, especially the last one where Europe's thing is done, but it doesn't mean that you cannot do it because it's basically length contraction and time dilation and velocity addition. It's standard. It's you do this everywhere. If you have any confusion, go back to the last year's lectures and you should be able to fast forward and there are something. But it's, you won't see anything relevant. Like homework is independent of the lecture, right? So you won't. So attempt on it, and if necessary, we can do this. You're very quickly going to be losing. How about this? I think I'm still okay. I'll do. Let's postpone the homework by a day. So let's make it Tuesday. Okay. Unless you guys work on it and you finish it, then I can proceed. If you say that, yeah, we understand Lorentz transformation very well, that should be okay. So how about this? Let's make the homework due on Thursday. If you're struggling, then I'll come and help you. Okay, so homework is due on Thursday. Okay, so I changed my mind for a moment and then brought it back. Okay. Okay, so it was I was everywhere, but I think it's probably useful discussion from that.